No. I'm guessing they're running on the theory that since the lab report is due at the beginning of class, if they're not here on time, they won't be held accountable. Code.
We're on time. I'm giving up on this.
Okay, so Lauren Lee and Alina and Maggie came here, but still no Tioni. Okay, anyone else have the lab papers?
Not the lab before class starts.
Yeah, that's it. All right, so this is all the lab reports, right?
Yeah, 1 second. I can find out.
Do you have your lab reports, Tom? That's all. Okay.
Are you going to get through all of it?
I'm done.
I was up like an hour this morning and like 3 hours last night.
I like your power.
Yeah.
All right. Let us begin. Now that we've collected that. So, start with the clicker question. What force keeps the planets orbiting the sun?
I will do it. My money. Hold on. It's coming. Gotta change this. Just leave it. Just the force.
Obviously, Satish and I were thinking the same line.
Has anybody told you today that they appreciate you?
No. Glad you approve of that. Okay, for some reason it's not showing me who's answered, but we have, now everybody's answered, so. And it's also not showing me the answers you gave. Okay, so I don't know how I end up with things not working with the clickers. The correct answer is the force of gravity. Gravity is what is pulling all the things together. And it's that force of gravity pulling in on the planets, holding them in. Okay, energy. I think I asked you guys like a week ago, what does energy mean to you? And I just asked you to be honest, right? On the Flip Friday, last week's Flip Friday. And so now we're going to try to learn and make sure we understand what it means, because we were using the word energy before we had any description of it. So what does energy mean to you? You know, when you, oh wait, I went forward on the wrong slide. You didn't see that. I have it here, which is a bad sign because it's not supposed to be on that one, which is probably why nothing worked. Now that I think about it, well, yes. I opened the wrong one. That's why it didn't show us the answers.
So should we do it again?
I will have you do it again. I'm sure you're going to all get the right answers this time. But just so we have it right. It's like, wait a minute, there's something so wrong. clickers. Okay, go ahead and answer again this question here. Everyone be right this time. And yes, it's now doing what it's supposed to be doing, showing me.
You said something.
Labor, it didn't record yours. In channel 33? There we go. What was that?
Did you say something about how the force for inertia is used?
How what?
Something about inertia as one of the forces that would keep the planet orbiting?
Okay,
Like how it was always falling?
inertia is the propensity of something to continue traveling at a constant velocity. Inertia is not a force.
Oh, okay.
So inertia would just make something go straight, and then a force will make it deviate from that.
Okay.
Okay, so now defining energy. Energy is, the first answer for energy is kind of annoying. It's the ability to do work.
Hey, that's what I put.
Is it really?
Yeah.
That's the definition. Something has energy, it can do work. But then that begs the question, what is work? So work is, hey, how about if I say transfer of energy? Does that sound like a perfectly circular answer? Thank you.
Yeah. Kind of.
So work is best typified by looking at its general equation, force times distance. So we've already learned what force is. Force is anything that pushes or pulls, right? And so if I have something that pushes or pulls and covers the distance, now there's another piece of that. It needs to be a push or pull that's parallel to the distance it traveled. Let me put these with the other stuff for Reese. Okay, sorry about that. So work is force times the distance something moves, so delta x, and it has to be delta x in same direction as the force. So simple example, if, stand up, Dylan. If Dylan's here, and I come and I push on him, and he doesn't move at all, I didn't do any work on him. But if I push and he moves, then I did some work. Right? The work is putting a force that makes something move. Energy is not that, that's all I can get. Energy is having the ability to do work. So you can have the ability to do work for a number of reasons. You're saying on your phone, that's what you're looking for.
Oh, no.
We can have energy because something's moving. For instance, if I were to make Dylan stand up again and I came running at him, when I actually hit him, would I do work on him? Yes, I would. I would put a force on him and it would make him move. And so I had energy because of my motion. We call that kinetic energy. Kinetic means in motion. We can also have potential energy, things like if I take this mass, I will not drop it.
Oh.
But if I take this mass and I let go, it's going to start moving downward. Why? Force of gravity is pushing it down, and then it's going to have a distance it covers. Gravity is going to do work on it. We say that it has a potential energy based on its position. Because of its position, gravity can do work on it. And so that's another type of energy we talk about, potential energy, where you can have work done because of the position. Now, those are the only two fundamental types of energy, but when you get to something like the air around us has a bunch of tiny molecules that are moving around. Oh, here's the equation for kinetic energy. That's the energy in motion. If I was running, my kinetic energy would be 1/2 of my mass, that's how much of stuff I have, multiplied by my speed squared. Notice if I double my speed, if I were to run twice as fast, what happens to my kinetic energy? 4 times bigger. So a big guy is scary because he has a lot of mass. A big guy who's fast is extra scary because the kinetic energy scales with speed squared. A small guy who can run really fast might be able to have more energy, deliver a bigger hit, than a bigger guy who's slow. Because the speed is actually more important than the mass for the energy that you have that you can deliver. And I say that you can deliver because, of course, I'm thinking of football now. And people whacking into other people. Okay, now, I was talking about the energy in the molecules in the air, which I hope is where this goes. Yeah. The molecules in the air, each one is moving. And since each one is moving, each one has its own kinetic energy, its energy of motion. But there are on the order of 10 to the 24, 10 to the 25 molecules in this room. Question? I'll just write it here.
What's the name of this PowerPoint? I imagine it's probably going to be on the...
What's the name of it is Lecture 10. There's on the order of 10 to the 25 molecules in this classroom. And those 10 to the 25 molecules are all moving. It's impossible for us to calculate the total energy for each one of those molecules. Right? We might be able to count a few hundred, maybe 1,000, but not 10 to the 25 or so molecules. So instead we use statistics to use a number that represents that kinetic energy. And those statistics, what we call statistical physics, is also known as thermodynamics. And the temperature is actually a measurement that tells us what the average kinetic energy is of the molecules in the room. So the higher the temperature, the higher the average kinetic energy. So when it gets hotter, that means the molecules are moving faster to give them a higher kinetic energy. If you think about it, the maximum speed a molecule could have is approaching the speed of light, which is ludicrously fast. It's not something practical. So for all intents and purposes, the speeds can go up and up and up. But what's the slowest speed the molecules can have? Well, 0. They can be at rest. And so there is a minimum speed that the molecules can have, which implies a minimum temperature. And so absolute 0 is the name for the temperature. Now, quantum mechanics says that they can't actually reach rest. Right? It's well beyond this class on that theory. But absolute 0 is the theoretical lowest temperature you can reach. Now let's... Question?
I was going to say, why does that theory take quantum mechanics to arrive at?
Well, because we don't have any other theory that gives us that. Quantum mechanics is treating particles as waves and looking at their wave nature. And it is very useful for talking about small things. When we talk about big things, quantum mechanics works, but it gives the same answers as our general physics, so why would we do that? But for talking about things that are small, quantum mechanics is the only way that we can really calculate what's going on. And basically, what you find out is quantization, that there's only certain energy levels something can have, and the minimum energy level isn't 0. The minimum energy level is still having some energy, and that's why they can't be completely at rest.
It's almost asymptotal, right?
Well, not when you get to the quantum level, no. In the classical level, yes. Okay, temperature scales. When you measure something like the temperature outside today, what scale do you use?
Fahrenheit.
Kelvin. Yeah, no one.
I can never remember how to spell under Celsius's name. Is that a C or an S right there? I mean, I know I wrote a C, but it's really supposed to be a C? Okay. I just don't want to pretend like, oh yes, I have this new spelling that everyone should know. So we have these different scales. Just a quick background. Fahrenheit scale. Fahrenheit scale, Fahrenheit was a German dude. And there are different stories about how he came up with this temperature scale. The one in my textbook in graduate school, which I'm guessing is not right, said that he used the temperature of seawater and ice mixture for 0 and his wife's body temperature for 100. Other sources say he uses the body temperature of a bovine for 100. Either one makes me laugh, and if you merge them together, I really, really laugh. But he had what we call a centigrade scale, 100 degrees between his two reference points. And so his had, what I call it, ocean water / ice was 0 degrees Fahrenheit. And he had wife's body temperature was 100 degrees Fahrenheit. His wife was, okay, Satish. I am sure this is not Celsius, yes.
Celsius is with an S.
It is with an S? Okay, so I'll change it. Satish.
Anyone can make their own then.
Sure.
Cool. So this is like, well, my question is then like his difference in degree is like 100% arbitrary.
Yeah.
Because how would you accurately divide the temperature between?
Well, you use something, for instance, a gas that expands as you heat it up, and then you use linear gradations between your two reference points. So that's how Fahrenheit came up with his. Now, Anders Celsius, I have to split his column in two, because he said, let's let boiling water be 0 degrees Celsius and freezing water be 100 degrees Celsius.
Really?
Hey, don't make fun of my Swedish, non-ancestor. Does that work for you? Why not?
It's backwards.
It's backward.
It's counterintuitive.
And so he died, and a year after he died, scientists said, well, that doesn't make sense because there's an absolute 0, and we're working up toward that. And so they were just recast, so boiling water was 100 degrees Celsius, and freezing water was 0 degrees Celsius. So Celsius's original scale is not the one we use anymore. Furthermore, even that version of Celsius's scale is no longer the one we use. This one here is technically called a centigrade scale, just like that Fahrenheit was also a centigrade scale because it had 100 gradations between the reference points. This is purely esoteric for you, not something you have to know. But the definition of the reference points for the Celsius scale was changed when I was in high school to have the temperature of the triple point of water, which is 0.01 degrees Celsius, as the lower reference point. So it's now 99.99 degrees between the two reference points instead of 100. Hence, it's no longer centigrade, and technically, Celsius scale is not centigrade anymore.
Oh, I wonder what we're going to do in Spanish, because in Spanish we never called it Celsius, we always called it centigrade.
Then you guys are just lying to yourselves.
Generations to come over.
It's a small point, obviously, not important but curious. And then we have the Kelvin scale. The Kelvin scale is a scale that is an absolute scale. Since there is an absolute minimum, the Kelvin scale says, okay, we're going to set 0 degrees Kelvin is the absolute minimum temperature. And it turns out that the absolute minimum temperature is minus 273.15 Celsius. And so if we put these things with comparable absolute 0, I don't remember. It's like minus 458 in Fahrenheit, but I could be off by a couple degrees. And it's minus 273.15 degrees Celsius and 0 degrees Kelvin. We don't show a degree Kelvin or say degree Kelvin, though. We just say 0 kelvins. I know I said 0 degrees Kelvin, but then I realized I just said it wrong. So absolute zero is 0 kelvins, and then freezing water is at 32 degrees Fahrenheit, 0 degrees Celsius, 273.15 kelvins, because the Kelvin scale uses the Celsius scale, just offset by 273.15. And then we can go to other things like body temperature. It turns out body temperature is 98.6 degrees Fahrenheit. That's an average. It depends on the time of day. It depends on where you are. It depends on who you are. But that's an average value we use, which is around 37 degrees Celsius. And that would make this about 310 kelvins. Right? Those are rough numbers for the Celsius and Kelvin. Question?
Right, isn't it off by 273?
Yeah, that's 310.
Okay. Yeah.
Sorry.
Yeah.
And then boiling water is 212 degrees Fahrenheit, 100 degrees Celsius, and 373.15 kelvins. So just some comparisons between the different scales. In science, we use either Celsius or Kelvin. Since they have the same shifts, a change in 1 degree Celsius is the same as a change in 1 Kelvin. In many ways, they're interchangeable. But Kelvin is the one that we rely on the most. Kelvin is nice because if the temperature is close to 0 kelvins, you know that you're close to absolute zero, that the molecules are close to rest. As the temperature goes up in kelvins, they're going faster. And there are conversion factors. The temperature in Celsius is equal to the temperature in Fahrenheit minus 32 times 5/9. It's a simple relationship because you have a difference of 180 between these two numbers and 100 between those two. 100 divided by 180 is 5 divided by 9. So that's where the 5/9 comes from. And 32 degrees Fahrenheit is 0 degrees Celsius, so that's why it's temperature Fahrenheit minus the 32. And temperature Kelvin is just temperature Celsius plus, or minus, plus.
Plus negative.
I was wrong. It's temperature Celsius plus 273.15. So those are how to convert between them. So that's how we measure, that's the units of measuring temperature. And temperature is measuring, well, what is it measuring? Let me ask instead of telling.
What is temperature measuring?
Yeah, what's it measuring?
It is measuring the average kinetic energy of the local molecules.
Yeah, the average kinetic energy of the molecules. Now, it is important to know that the average kinetic energy of oxygen molecules and hydrogen molecules is not the same as the average kinetic energy of, well, those are going to be different, and the average kinetic energy of, like, iron molecules. For the same temperature, those are going to be different. So it's per substance. It's proportional. It's not for everything. Okay, I already talked about potential energy. I can just skip that. That's just reiterating what I said. That did have, I should go back. Don't worry, you couldn't have answered anyway. I should talk about here, I noticed, well, this is conversion of potential energy. If I let go of something that has potential energy, it will naturally go to the lowest potential energy available to it. So once again, if I were to take this mass and let go, it would fall to the floor because that's lower potential energy and that's as low as it can go to. That's a general rule in all of physics, then our energy is going to try to go to the lowest available. It actually tries to go to where you distribute the energy equally in all of the different forms.
Doesn't everything have potential energy though? Any mass?
Any mass has a potential energy in the form of mass. Mass is a form of energy.
Yeah.
Yes, it does. And that is a potential energy, but to release that takes a very special situation.
Right.
It's not accessible for it to do that. There's not an avenue for it to do it in a normal situation, so it doesn't do it. So if it could, it would. But I mean, that's what fusion is. That picture back there talking about fusion. You have two protons, and the reason that's up there is because that's the first thing we're going to read. Of my 4 posters, that's the first one applicable to astronomy. In the sun, you have protons that come flying toward each other. There is a force pushing them apart because they're both positively charged. But if they're going fast enough, you can make them come and touch anyway. And if you can make them come and touch anyway, then you make it possible for them to merge and release some energy from mass. So the mass drops when they do that, and it releases energy, which is what gives us sunlight.
And atomic bombs.
And atomic bombs. So it will do that if it's possible, but you have to have special situations to make it possible. So it doesn't happen in our bodies because we don't have that situation.
I was just, you kind of answered my question.
Awesome. And clearly, right?
More or less.
Okay, so energy can be converted from one type of energy to another. One of the fundamental rules in physics is that energy has to be conserved. We can't use up energy. We can only change it from one type to another. Now, some of you might say, wait a minute, why do they talk about, having energy problems if you can't destroy energy? The problem is we can move energy from one type to another type, but it's often hard to move it back. For instance, we use in my automobile gasoline to power that automobile. That gasoline is storing energy in chemical bonds. The bonds between essentially the hydrogens and the carbons in the chains in the gasoline is where the energy is stored. And when we burn the gas, we have an oxidizer, oxygen from the air, that pulls those hydrogens off, and it's forming water and smaller molecules of carbon like methane. And, well, actually it's forming more carbon, depends on how well it's burning. But it's forming smaller molecules and releasing energy. It takes a lot of energy to return it to gasoline. And so if I use up all of the gasoline or all of the oil, which is where we get our gasoline from, then I'll use up all of the supply of that kind of energy. And it's hard to replace it. And so one of the things we try to move toward in society is renewable energies, things that we can replace. Sunlight is more than 99% of our energy budget. That is the Earth's energy budget. More than 99% is sunlight. So there's a lot of that. If we can use sunlight, that's completely renewable, despite what some Congress people might have you believe. You can't use up the sun's energy and then the sun doesn't have energy. The sun's going to radiate that energy whether we use it or not. And that's renewable every day. And so that's what we're talking about when people talk about energy crunches and that kind of thing. We want to go to energy sources that we can replace instead of ones that we can't replace. Question?
What's the 1% of energy? You said 90%.
Radioactive energy released from radioactive materials. Okay, clicker question number 2. An iron bar is removed from a furnace and placed on an anvil. What type of energy does the bar have?
I mean,
We are taking into account everything we can. Okay, everyone has answered. So we have 0, 7, 1, 0, 3, 0, 3. Okay, so out of 14 responses, 1/2 of the people chose this one. Let's see. Thermal is also here, and thermal is also here. So 10 out of 14 had thermal in their answer. Does it have thermal energy? Yes. What would be your indicator that has thermal energy? Yeah. If the temperature is not absolute zero, it has thermal energy, right? It was heated up to make sure people realized, yeah, it has thermal energy. But even if it had been room temperature, it still would have had thermal energy, just not as much. So it had to have thermal energy. Now, kinetic energy. What is kinetic energy? Energy in motion. As long as you are considering thermal energy as a type of energy, then those molecule movements don't count as kinetic energy. Kinetic energy is going to be the bolt thing, like is the iron rod flying across the room?
Across the galaxy.
Okay, across the galaxy. There is a level where you can say, wait. The Earth is not perfectly stationary. The Earth is orbiting the Sun. The Sun is orbiting the Sun of the Milky Way galaxy. And so if you use those, then you would have a correct argument for it having kinetic energy. Also, the Earth is rotating. Forgot that one. That's another one. Usually we consider the Earth reference frame to be stationary and say, okay, so there's no kinetic energy. But, right, that's one that can be argued depending on what you want to choose. And then we have gravitational potential energy. Is it in a position where there is somewhere lower it could possibly be? Yeah. So it has to have gravitational potential energy because if it got bumped, it could fall down to the floor. So it has to have this, has to have that, may have that. So the answer that I considered correct was this one that had both thermal and gravitational. And like we said, this one had... Okay, I didn't notice that this one here had thermal in as well because I wasn't thinking. I didn't see the word thermal. This one here could have been argued based on your reference frame arguments. Yeah.
It could be confusing with gravitational isn't using the whole one, the whole wood. Instead of using gravitational potential, you just put gravitational. So that kind of confused me at first.
Well, it said up here what type of energy.
Isn't gravity not an energy, but the potential of gravity is?
Gravity is a force, and there's a potential energy associated with that force. Okay, moving forward. Here is pictures showing what's happening there in the stars to produce the energy. You have protons come together. Normally, they're going to repel each other. So here the protons didn't hit. They deviated away from each other. That's what normally happens. But at high temperature means those protons are moving faster. The protons can actually be moving fast enough to hit each other. You actually have two conditions necessary for fusion to occur. One is high temperature so that the protons are moving fast enough. The other one is high pressure, so the probability of two protons hitting is high enough, right? Because if you had only one proton, it would never hit another proton. It's pretty obvious. If you have 10 protons in this entire room, the chances of any two of them colliding would still be pretty close to zero. But as the pressure goes up, you're having more and more protons passing through, and so the chances of collision are bigger. So you need both high pressure and high temperature to actually make this occur with any continuation. Yes?
It might be a kind of a side question. It might be covered later on in the semester. But at what point does it become plasma?
Well, plasma is an ionized gas. And so everything in the sun is a plasma because the molecules are moving too fast, have too much kinetic energy, electrons are ripped off of all the protons. So all the protons are naked protons, all the electrons are just hanging out free. And so that's why it's a plasma. And you can call it a gas, you can call it a plasma. People like me won't care. I care about things like people getting weight and mass confused. There are some people who are all, no, it's an ionized gas. That means it's not a gas, it's a plasma. So, there you have it. Okay, angular momentum. Who wants to come be a guinea pig?
B.
Okay, come be a guinea pig, sir.
Set taking to the team. You're gonna get beat up like you want.
Your job is very simple.
Don't fall off.
Sit and spin. Okay, so we're going to start off with Satish. Just sit there. We'll be good. Okay, so Satish is here, and I'm going to just spin him gently. And now put your arms out. Out.
Out.
What happens to speed when he puts them out?
Slows down.
Bring him in.
Well, now he's going to.
Can't really tell, right?
Yeah.
I used to have some heavy masses. These aren't so heavy, but these will have to do.
We can just look at an ice skater.
We could, but it's a lot more fun to have Satish do this than look at ice skaters. So put them out. Pull them in.
Oh, good shield.
More obvious, right? Now, put your arms out. And I'll spin him with his arms out. Now pull them in.
Oh.
And of course, when you use heavier masses, it's more fun. That's all. Sorry. Fun is over.
Oh man.
What was going on here? I mean, in physics class, we spend lots of time trying to discuss what happens and causes these kinds of things. What do you think is going on?
Pull the mass with the center of gravity.
I think
Well,
that
it's not toward the center of gravity, but it would have to do with pulling the mass in toward the axis that who's rotating around.
aerodynamics are pushing more.
No.
It's not aerodynamics.
It's got to play a factor in it, right?
No.
Well, aerodynamics as well as the friction in that thing play a factor in him slowing down overall, but not a factor in him speeding up.
No.
So what's happening is he had what we call angular momentum. He was rotating, and momentum is the propensity to continue doing what you're doing. It's a similar concept really to inertia. Linear momentum is mass times the speed. Angular momentum is mass times the speed times the radius. So in this case, if he's rotating, if he has the masses in close to his chest, those masses are going around with a very small radius and actually a small speed, because the speed is going to be the circumference of a circle it prescribes divided by the period. When he puts them out, then the radius becomes much bigger. If the radius becomes bigger and the angular momentum isn't changing, then it's going to have to slow down further, and so he slows down when he puts them out, brings them in, and he speeds up. And so all of that was occurring because of what we call conservation of angular momentum. And you might be saying right now, you know, we have a lot of physics in this, don't we? Yes, we do. There is a reason why astronomy is a physics class. Because everything we know about astronomy starts with what can we learn about nature here on Earth, and then determine what's going out there from that information. So we have things like a star is believed to form from gas that collapses in. Now, if that gas was all out here in a big nebula and going around slowly, as the gas collapses in, what's going to happen to the speed at which it's rotating? It'll be quicker. And so we can understand why our stars are spinning and our everything is spinning, because any small amount of rotation gets greatly magnified when it collapses down. And we'll learn later about things like neutron stars or pulsars. A pulsar and neutron star are actually the same thing, but a pulsar is spinning rapidly and its poles are flashing us, so we see the flashes of light each time it comes around. Yeah?
For that equation, what does the L stand for?
L stands for angular momentum. I don't even know why L stands for angular momentum. I learned it when I was in high school, and now it just seems natural. But no, I have no actual understanding of why L stands for angular momentum. So it's an important concept, something we're going to need to understand when we talk about things like, why is a pulsar spinning so fast? Now here's the example with the skater, or, we could take a physics teacher. A physics teacher can spin slowly. Ooh, that's exciting. But notice when they spin, they start with the arms and leg out. And so they start with everything out, and then they pull it in, and they spin a lot faster because they have those things out there going slow. Pulled them in, radius got small, the speed of rotation had to pick up. And by the way, when you do something like Satish did there, you start to get some respect for those figure skaters. I mean, they're boring to watch, but I can't imagine staying on my feet or having the power to do the tricks they do.
On skates.
Yeah.
I don't think.
Good, I do.
I don't think often, but when I do, I think that it's not correct to say that the speed increases.
Well, you can
I
say
think the RPMs increase.
the speed is going to increase, but it's easier to talk about the angular velocity.
So, acceleration takes place then when your hands are pulled back in.
Yeah.
Because you're speeding up.
Well, it's acceleration both ways, but one's acceleration making you speed up and one's acceleration making you slow down. Satish and then Megan.
I am confused because why do rotations per minute increasing not equal speed increasing?
I know we have a question open here. Okay, omega is what we use for, well, radians per second, but rotational speed. And that's the speed divided by radius.
Right.
And so what we have is angular momentum is equal to mvr or mr squared omega. And so if L is constant, if R increases, both omega and V have to decrease. But you see the rates at which they decrease are different.
Could it be better explained with like a CD drive? Like a disc? The outside of the disc is moving.
Well, yeah, an outside of disk is moving for the same omega. The outside has a bigger speed.
Right.
But you still have the same, the speed is still going to increase when the radius gets smaller if you keep the same angular momentum. It's just a different rate for the speed as it is for the angular velocity. Okay, we still have 5 people who haven't answered this question. A student sits on a spinning platform holding 5 kilogram masses near his or her body in each hand. What happens to her or his rotation rate when she or he extends her arms? In this case, it was Satish, so it would be all he's and his. Is it not working still? It doesn't. Oh, yeah, different number. Okay, we're good. Okay, good. Everybody paid attention. They saw what Satish did. That principle, like I said, it's an important principle that we don't want to forget because it's going to come up later as we're learning more about astronomy. Now we're going to talk about the atom. We've already done a little bit about light, but really to understand light, we have to understand what is known about the atom. So here are some models of the atom. Going back to Democritus, for whom I believe we have democracy. You all know that the United States is not a democracy, right? Everybody's learned that?
It's a republic.
Yes, we are a democratic republic.
For which it stands.
Just a republic.
Well, no, we're a democratic republic because our representatives are democratically elected. It really annoys me when people say that the United States is a democracy. But yeah, anyway, so Democritus was the person who came with the idea of the atom. Democritus said that if I take something like my stylus and I break it in half, I'll have 2 smaller pieces. And if I take one of those and I break it in half, I'll have 2 smaller pieces. And if I keep doing that over and over again, eventually I'll get down to where I've got the smallest piece I can break. And I can't break it anymore. And he said, once I've got to that smallest piece, it's indivisible. And so he called that smallest piece indivisible, with liberty and justice for all. Or an atom. By the way, isn't Constitution Day next Tuesday?
That was yesterday.
Oh, it was yesterday. Okay, wow.
You failed your American history
No, I failed to go to what the meeting formerly known as chapel.
Yeah.
I know. 40 years of calling it chapel is hard to change. Okay, next up we have J.J. Thomson. J.J. Thomson in 1897 discovered electrons. And he said, woo, electrons are in matter. And if electrons are in matter, then matter must be like this goo with little negative charges in there like raisins in pudding. Now, here in the U.S., plum pudding is not something we have much familiarity with. So I tend to call this the oatmeal with raisins model, where the matter was generally oatmeal, and then you have these little raisins that are the electrons. Now, notice that it's only 12 years later when Ernst Rutherford, I don't know if it's Ernest, I've seen it both ways, when he has Marsden do an experiment for him where he takes gold foil. Gold is malleable, which means you can hit it with a mallet and it will just squish instead of fracturing. And so because it will squish instead of fracturing, you can make gold very thin, hence gold leaf. And so they made a thin film of gold and fired little alpha particles at them. Helium nuclei is what they are. And what they expected was, if it doesn't hit an electron, then it'll just go through, hardly change, maybe slow down a little. And if it hits an electron was so much less massive than the alpha particle, it will slow down just a small amount. But when they did the experiment, they found most of the alpha particles didn't slow down a bit. They just went straight through, and some of them bounced straight back or at crazy angles. Rutherford described his shock at this outcome as akin to if you fired a cannonball at a piece of tissue paper and it bounced back at you off of the tissue paper. Right? They expected it to go through like a cannonball would through tissue paper. And so he said, there must be something that's really massive in this gold. And so he came up with a model that we call the planetary model. This is astronomy. It's kind of nice that we have planetary here. The planetary model says that you have a nucleus with electrons doing circular orbits. Now, this was well after the time of Copernicus, the Copernican revolution. So he should have gone with Kepler's elliptical orbits, but he went with circular orbits. And almost instantly, scientists saw problems with his theory. Niels Bohr came over and worked with Ernst Rutherford, and just 4 years later, Bohr came up with a quantum model that said that the energies that the electrons can have orbiting the nucleus are only specific energies. Now, more specifically, what he truly said was they can only have certain angular momenta. Remember the angular momentum, the mass times velocity times radius? Only certain angular momentum were possible, or momenta were possible according to Niels Bohr. He just put that out there as I say this is so. Not with any scientific backing for it. And so we call that a quantized model because it said only certain angular momenta levels, which resulted then in only certain energy levels and only certain radii for the electrons. So what's different between the Bohr model and the Rutherford model is the quantized levels for angular momentum, for mass, for radius. There are still problems with the Bohr model. Plenty of problems, but much smaller problems. And so our standard model using particle theory and quantum mechanics says that we have the nucleus and we have electron cloud. We don't know where the electron is. We don't know what path the electron takes. But we can calculate still its angular momentum and its energy and whatnot. So we've gone through a number of iterations of the atoms. And the current model is the one that we played with when we were looking at the energy levels on Friday. We were looking at the energy levels specifically for electrons bound to a hydrogen atom. I believe this is another clicker question here, but waiting for it to pop up. Nope. So the pictures you've been looking at we have different levels. Illustrated here as elevator. I like to think of these levels kind of like in a closet. So you put your shoes the top shelf of a closet. And then an earthquake happens. What's going to happen to those shoes? They're going to fall down. What are they going to do? They fall, they go where? Down until they get to the lowest available state, right? The floor. And when they hit the floor, you hear the thud, the sound. Well, that's exactly what's going on with electrons. If you raise electrons to a higher energy level, and there's a lower one available, there will be enough disruption, something will disrupt them, and the electron will fall down to an available level. And when it does, it gives off energy. That thump, the sound you heard, was energy going away that originated with the shoes falling to the ground. Right? That energy has to go somewhere. It can't be destroyed. Well, we have so much energy involved with the electrons falling that what comes out is light instead of sound waves. So light waves are produced when the electrons fall from one energy level to the next. If this is not a clicker question, we'll leave now, but I think it's a clicker question. Come on. Nope. Okay, we'll leave now. We'll start with the clicker question. Well, we'll start with this in the clicker question next class period.